Let me just put some stuff on the board just to make sure that neither you or me are in the wrong room. So this is going to be quantum mechanics 1. And my name is Cemal Yalabık. Okay, and I live somewhere on the second floor on the physics building. There are a number of details that you need to know about the course. They are all on the course web page. I sent you an email yesterday. You should have received it. There's at least one student whose email bounced back, so make sure that your STARS email is a valid one. Okay, sir. So there are a number of points, especially about attendance. There's very strict attendance requirements for this course. You can't miss more than 6 hours. There are exceptions to it, but they are all described on the web page. There's also policy for homework. Again, they are all in detail reachable from that web page. I'm going over this because people sometimes don't read these things and then they discover what's going on after the second midterm or whatever. Okay, so for example, for the homeworks, I also evaluate a geometric average, which means I multiply all the grades together and take the nth root, which means that if you have a 0 in one of the homeworks, you get a 0 for the geometric average. Okay, so all these stuff, they are on the web pages, and please read through them. Okay, those are important information. Okay, apart from that, we'll have the standard stuff, the 2 in-semester exams and a final. There will be occasional homework. And, okay, so the homework problems and examples that I solve in class, and every once in a while I'll just assign something as an exercise. Exercise means something that you should do, a homework that you should carry out, but it's not going to be collected, okay? But those things make up stuff which make you easier to learn, because unless you do this stuff yourself, of course, you do not learn it. Okay, so one point that comes up almost every exam is that students come to me and say, we understand everything. We can follow all the algebra, we can follow the notes, etc., but I couldn't solve the problems in the exam. Okay, and then I asked them, did you solve any problems on your own? Okay, because that's how you know whether you have learned a subject or not. That's how we test you, whether you have learned or not. Okay, so I recommend that you do all the exercises that I give you in class. Another point is that I usually go at the pace of the class for quantum mechanics 1. Quantum mechanics 2 is different. In quantum mechanics 2, we have to finish all the subjects which may also have overflown from the first semester. Okay, so the first semester I try to go at the pace of the class. So if you have questions, please ask them. Okay, don't worry about whether it's a silly question or whatever. In a class of this size, if you have a question that appears in your mind, statistically, you probably have 3 or 4 other students who have the same question in their minds. Okay, so be courageous and ask. Okay, there's nothing wrong with asking questions. The more questions you ask, the better you learn in class. So if you learn in class, that's of course a much better use of your time. instead of just copying notes and then going home and going over them, etc., to learn that stuff at that time. Try to learn it in class, okay? I'll make every effort that you learn it in class, okay? What else? Not much more, really. Do you have any questions about the structure of the class or the course? Anything that you want to ask at this point? Okay, and one point I'm uptight about, I'm against using cell phones in class, okay? So turn them off, okay? Just don't leave them on your desk looking with one eye, okay? Okay, it can stay on your desk, just turn it over, okay? I don't mind, okay, where they are, as long as you don't use them. Okay, so I guess we'll start. So customarily, every class on quantum mechanics starts with a simple description of what happens in classical mechanics. Okay, so in classical mechanics, we have coordinates and momenta. Okay, so coordinate of an object is going to be given by a vector. Okay, so x cross y is z, and I have my particle. Okay, it has some mass m, okay, at some vector r, which is going to be, of course, x, y, and z, and say this is the position of the object at time equal to 0. Okay? We also know its momentum. So suppose this is the momentum, again, at time equal to 0. And what happens next is just deterministic motion of this object, okay? So it just moves in the space, and the rules for finding out where the object is a little time later is very easy. You just, if you are interested in the rate of change of the position, how that changes, well, mass times that, of course, is the momentum, okay, one of the variables that you know. How does the momentum change? Well, that's just the force acting on the object. So there's some force field here, which we can determine from the gradient of some potential energy. Okay, so there's some potential energy in which this object is moving. So someone kicks it, it starts moving, and in that potential energy field, okay, the object moves according to that. So I don't remember if you took the Physics 124 from me or someone else. Was I your instructor in the freshman project course? So you did 2 homework, right? I hope you remember, okay, from 2 years back, that you just follow the motion of an object, okay, due to some force, etc. So everything is deterministic. So if I know the position of, say, Earth and Mars and Saturn and Jupiter, whatever, at time equal to 0, I can calculate it to a great accuracy for several thousand years. Okay, it's quite impressive and very accurate. So it is all very deterministic. So, but it is not correct in every limit, especially in the limit when you go to very small sizes and corresponding energies, this system starts to fail. So what happens if I have a quantum mechanical system, the particle now, let's say something like the electron, can no longer be represented by a single point, it has to be represented by some sort of wave function. Okay, so this wave function is complex, so it is shown by psi, but because it's complex, it has a real part. Okay, so that looks perhaps something like this, I don't know. And then it also has an imaginary part. Okay, so imaginary part of psi is perhaps something like that. Okay, so this is the wave function at time equal to 0. So what happens to it? It moves. Okay, so at a later time, it ends up in a different place. So let me put my red and blue stuff over here again. The function, which has these oscillations also, okay, it's like a wave, and this is psi for t greater than 0. So this psi, complex quantity, obeys a wave equation and just moves in space. Okay, now how do we use this object? Well, let's just see what would happen if I was looking at it as in one dimension. Okay, so this is our psi. Again, I have to specify the real and imaginary parts separately. Okay, so the real part is blue. Okay, so the real part is going to be perhaps something like this, and the imaginary part is going to be something related. So if the particle is somewhere around here, both the real part and the imaginary part will be near that point. Okay, so this is my psi at time equal to 0. So what happens when I look at the system at a later time? Well, the object has moved, right? So red part is the imaginary part. So now it is somewhere over here, and not necessarily the same shape. I am trying to draw arbitrary shapes, but drawing arbitrary shapes is not always that easy. Okay, so that is our psi for some time greater than 0. Okay, so to use this, we can use this information in various ways. We'll learn how this develops. You see here, we have these set of rules, which we call as Newton's laws. And here, what takes the wave function from that time to that time is the Schrödinger equation. Okay, so the Schrödinger equation is a differential equation. It's a differential wave equation. And in this course, we'll mainly study the solutions to the Schrödinger equation. So let's see how we use this thing. So what I do, simplest thing I do, is I look at the magnitude of psi squared. So now this is a real, number, and it's a real function and is positive definite. So this is magnitude of psi 0 squared. So at a later time, when I look at the magnitude squared of this, its shape may have changed, but I end up with psi t greater than 0 magnitude squared. And my interpretation of what this wave function is that if I just look at this, it is equal to probability, which will be a function of x and, in general, time. So this is the x behavior at time equal to 0. This is the x behavior at a greater time. Okay, is all of this clear? Okay, because the more difficult parts of the theory are usually in the simplest parts. Yes?
Why the magnitude of psi is equal to probability? I mean, why we evaluated them on the probabilistic model?
Okay, that's a good question. Let me first say what we mean by this pxt. Okay, so if I have this p, and if I look at the value of this p at a certain time, here it's time equal to 0, but in general I have something like this. Okay, so if I look at psi x t, okay, magnitude squared dx, okay, where dx is some small quantity here, okay, is the probability that the particle is between x and x plus dx at time t. Okay, my handwriting is not the best, but I generally read it. Okay, so probability that the particle is between x and x plus dx at time t. Okay, that's what we mean by it. Now, why do we say that? Well, that's one of the fundamental problems in quantum mechanics. How do we interpret this psi? Okay, so it is indeterministic. So this event says that quantum mechanics is not deterministic. And this lies as a fundamental statement of quantum mechanics. Now, I must say this is not the only interpretation of this psi. So everyone agrees that there is some sense in this Schrödinger equation, that it gives you this nice psi, from which you can evaluate lots of things. Okay, you can build things like cell phones and smartwatches and whatever, all the miracles of modern electronics technology with it. But how do you interpret, how do you interpret what is going on? What is the connection between this psi and reality? Okay? This is not something that is, I would say, definitely settled, but there is a strong belief about this interpretation. Yes?
Also, I couldn't understand what is the psi? I mean, is it a wave function of something, or a wave function of some phenomenon?
These are all very good questions. These are all for you guys to find out when you grow up a little bit more. Okay? So this psi is a complex function, so it has a real part and an imaginary part, so it has two components. It's a two-component wave, but the wave itself is not something that is directly measurable. Okay, we cannot actually measure what this value is or what that value is, etc., unless you make very imaginative experiments for very special cases, etc., to find what the phase of the wave function is and such things. But ordinarily, this is not accessible to us. Neither is this. Usually, this is a result of a calculation, it's a result of an abstraction. What is available to us are the results of experiments when you measure x. So we measure x and we get certain values. Each time we measure x, suppose I have something here which is sending all the same types of wave functions one by one. and I make measurements on each particle that's coming out, okay? And then each time I measure, suppose I wait for the same amount of time so that the wave function is always this. Each time I make a measurement, sometimes I get a value here, sometimes there, very unlikely, but sometimes there, never there, okay? So it fits this probabilistic interpretation. But there are other interpretations which are not so popular, okay? But they also sort of give you the same association between what we see and the mathematical abstraction. Okay, so the wave function itself is a mathematical abstraction. It tells us also, the theory tells us how we can use that to find what is going on. So we are looking at this thing one electron at a time, but usually if you have a technological product, something like a transistor or whatever, you have, okay, zillions of electrons flowing through, and you are just interested on the average, how many of them are moving, what their velocities are, and such things, okay? So it doesn't really matter that this is probabilistic or some other way. And so there are various ways of interpreting it. So what I would say, I have not made the statistics, but I would say 99% of the physicists who are working on quantum mechanics follow what is known as the Copenhagen interpretation. Okay, so obviously people were aware of this problem that, okay, how do we are solving all these nice problems and getting nice answers. We seem to understand everything in terms of numerics, but what is going on here? Okay, what's the relationship of this wave function with anything that's real? Okay, and in a conference in Copenhagen, so a number of physicists at least agreed to disagree, but the majority then ended up with this interpretation, which is what I have actually put down over here, that this psi is associated with a probability density function from which you can determine average quantities associated with the particle. Okay, so we'll be using that interpretation. Yes?
Different interpretations explain the same phenomena equally. What is the main motivation for choosing this one?
Well, it's the simplest one, okay, first of all. So the question is, maybe I should repeat questions because this is being recorded. The question is, why is this being adhered to? Well, it is the simplest one to play with, but again, there are people who are actually thinking about this. It is also a concern of the philosophers, because you can imagine that philosophers will also be interested in, there's this something mathematical and explains stuff, but we don't know what it is. And so for that reason, that is the most popular one, okay? It's the easiest one, and it has entered the textbooks and everything, so that's what we use. But there are other interpretations. For example, there's an interpretation due to Bohm, which is called the pilot wave, etc., which essentially tells you the same sort of thing, but it's much more difficult to actually follow through. Okay, other questions? Okay, so what do we do? For most of us who are practically in this job, we just say, okay, I'll just accept that this is a probability interpretation, and I'll do my calculations, and the results come out correct. So why worry? Okay, so this is also called the shut up and calculate. Okay. Okay. Method. Okay, so just don't worry about it. We'll not shut up, actually. We'll be talking about this because it's an introductory course, so we need to do this. But once you are into your research and you are doing all this work and trying to calculate, and your PhD advisor is telling you, okay, bring me the results next week, and then you go to your PhD advisor next week and you say, well, I sort of didn't believe the Copenhagen interpretation, so I was thinking about that for a week. Okay, so it's not going to be nice. Okay, so you just shut up and calculate if you are trying to get numbers out. Okay, but there is a certain amount of work also going into the interpretation of the wave function. Okay, any other questions? Any questions? Yes?
The Schrödinger equation basically describes the motion of the particle, but the particle itself is not reachable?
Okay, that's another interpretation. That's the Bohm interpretation. You have discovered the Bohm interpretation. Okay, one interpretation says particle is somewhere, okay, but we don't know it. So we sort of associate this wave function with it. So the particle is somewhere here. And we know how this wave moves. So the particle is moving along with this wave, but we don't know where it is. And then when we measure it, we find out where it is. The problem with this approach is that it's wrong. We know that the particle cannot be at a certain place. Okay, the type of approach that you are saying is that there are certain parts, there are certain pieces of the system that are unknown to us, okay, that are really there, but we do not know it. Okay, so those things are called hidden variables. Okay, hidden variables are things that are claimed to be inside the picture, but we cannot see them. And then when we make a measurement, all of a sudden the hidden variable appears. Okay, so this was a viable sort of explanation until actually quite recently. You see, when I say recently, after 1960 or something, we call these things modern physics, but quantum mechanics is now more than 100 years old, so it's not really that modern. But okay, so sometime during the end of this semester, or perhaps sometime during the second semester, we'll study something known as the Bell inequalities, in which we'll see that there cannot be any hidden variables. Okay, the particle exists as a wave, okay, until you make a measurement. That's what we know experimentally. Okay, so Bell's inequality allows us to experimentally remove the possibility of hidden variables. There would be people who would even disagree with that, but now we are coming to a region where we should at some point shut up. Yes?
Also, maybe I am not a silly question, but if my mind doesn't think me, I remember some Bell equation. Does Bell equation related to linear algebra?
No.
So I remember.
No, this is the. Well, okay, we'll see that.
Do we know the real part and imaginary part exactly what represent?
No, in fact, the real part, the imaginary part, are not really too important by themselves, because what we have is this psi, okay, which has a real part and an imaginary part. So let me write this psi real plus I psi imaginary. But you can always multiply in quantum mechanics by a phase, okay? a phase is something like e to the I phi. So what it does is it multiplies by something which looks like this. So now you have a new wave function. It has a different real part, different imaginary part because of the multiplication. But we know that the magnitude squared of psi is equal to magnitude squared of psi prime. So they actually correspond to the same thing. So multiplication by a phase, which mixes up these real and imaginary parts, really does not have a significance for most problems. Okay, so it's not really that relevant. It's the relative value of the imaginary part relative to the real part which is important. When you multiply by a phase, you are really rotating the real and imaginary parts together. Okay, so the relative phase doesn't change. Okay, other questions? We're doing on time. Okay, I should not, after talking so much about attendance, I shouldn't forget taking attendance. I usually give this all the way to the back so that it will eventually come back to me. Okay, thank you. All right. So let's now look at this wave behavior. How did this all start? Well, it actually started with photons. Let me just remove this stuff. Okay, so we'll not be talking too much about photons, but in this first lectures we have to discuss them because that's how quantum mechanics started. It started with photons, and experimentally people found out that photons come with certain bunch of energies. Okay, so this is so you already took a course on modern physics, so you know which experiments these are. Can you tell me which experiments led to the so that's yes. Okay, so photoelectric effect, which was how Einstein got his Nobel Prize, and one more. You may not know this. Yes. Yes, black body radiation. So as a result of these experiments, people found out that, so photon is an electromagnetic wave. Again, you see a two-component wave. There's an electric field and a magnetic field. Okay, but this time we can measure this stuff. Okay, the electric field and magnetic field are nice measurable quantities. And it has a wavelength, and also a frequency. And it comes, so the energy of this object is h bar, some constant, we'll talk about the magnitude of this, times this frequency of oscillation. Okay, so that is the energy of the photon. So you can have one photon, two photons, so if the number of photons that are coming towards me from these lights are zillions, so you can have zillions of them so that you can build up all this energy, but each photon that comes in has this amount of energy, All right, so this is a wave, so it looks something like, favorite function for waves is sines and cosines. So it has some x dependence, x meaning this direction. So, and if it's moving in the x direction, it also has this time dependence. So what are those k and omega? Well, we already discussed omega. These things specify the periodicity in x. So this is 2 pi over lambda, which means that if x is increased or decreased by lambda, what's inside the sign is increasing or decreasing by 2 pi. So it's periodic with 2 pi, okay? So we transfer that periodicity to distance, lambda. And this is similarly 2 pi over t, the oscillation period, right? So it's oscillating with time period t. Okay, so I can also write this as sine. Let me factor out the k, x minus omega over k t. But now you see this is a function in which x and t appear in this special form. And this means this represents a function which is moving in the plus x direction. Okay, so in fact this quantity here is the speed of the wave, which for photons we put in as c. Okay, why is that? Let's just look at that. If I have any function of x, okay, and is something like that. Okay, so this is my function of x at time equal to 0. What happens to this function at some larger time when t is not equal to 0? Well, it will just move over here. Okay, so this function here is f of x minus, okay, ct. Why? Because if I now look at this value of x, and so if this distance here now is equal to c times t, x minus ct will carry that point over here, will carry this point over there, okay, and that point over there. So that means this function, if I write it as an f of x minus ct, corresponds to a form in which this function is moving toward the right with speed c. Is this clear? Okay, because at time equal to 0, I get my f of x back. But at larger values of time, I have to move this in the x direction by ct, so that whatever this function is, it gives the same value at corresponding points. Clear? Okay, so this is something that's moving toward the right with speed c. Okay, so this says c is equal to omega over k. Let me, okay, perhaps I'll do it over here. C equals omega over k. All right, let's multiply by k. So c times k is equal to omega. So we have this interesting quantity, h bar times omega, which is the energy of the system. So let me multiply both sides by h bar. In fact, let me absorb the h bar inside. Okay. So this is the energy. And that's how it's related to h bar k. But now we have this simple relation from relativity, how the momentum and energy are related to one another. And here we have a massless particle, so it's very easy. Okay, so relativity just tells us that energy is equal to what?
P squared c squared plus m squared c to the fourth.
Okay, m squared c to the fourth. So this is just a relativistic equation. In our case, m is 0. So we get for the photon
Equals pc.
okay, energy is P times C. So energy has to be P times C, so this is P. Okay, so we have these two relations now. Energy is equal to h bar times omega. P is equal to h bar times k. Remember what k is. Okay, so we'll be using this so many times that this should at some point be something like a reflex for you, okay? So when I ask you what K is, it's not going to be your brain that's answering, it's your spinal cord, okay? So it'll say 2 pi over lambda, okay? So that's related to the wavelength. Shorter the wavelength, larger the momentum, therefore larger the energy, because they are just proportional to one another, okay? All right, so now that we have that, let's just put all of that stuff into our equation. So our wave, okay, which had the form K times X, well, in place of K, I can put momentum over h bar, X minus omega, and omega is energy over h bar times t. Okay, so this is the wave in terms of the physical parameters. Okay, now I have been putting this h bar in. How big it is in terms of physical quantities? Well, what I don't want to give you the h bar in SI units. It's not something very transparent, but we can associate the wavelength with the energy. Okay, so if you have a photon, okay, shorthand for photon is gamma. Okay, gamma means photon. So for a photon, if I have a wavelength of 0.5 micrometers, so that's quite short, so we can also write this as 500 nanometers. Okay, this corresponds to an energy of approximately 2.5 electron volts. Okay, so this is light at approximately the visible region. The visible light is about 400 nanometers. Okay, but for 500 nanometers, you get a 2.5 electron volt. Now, why am I giving these energies in electron volts? Okay, because that is a unit which is important or significant for materials in everyday life. What is an electron volt in energy? Okay, so if I take a battery, a 1 volt battery, 1 volt, okay, plus, minus. Here I have the electron, here it's the plus terminal. So if this electron takes a jump for some reason from the minus side to the other side through a potential difference of 1 volt, if it starts with 0 kinetic energy here, it will end up with 1 electron volt energy at the other side. Okay, so that's what we mean by 1 electron volt. Now, 1 volt or 1.5 volt or 3 volt batteries are common. That's because of the chemical reactions that take place in the battery. So if you have a battery at room temperature with some chemicals that are reacting, the energy transfer between these molecules are of the order of electron volts. Okay, so that makes a nice, reasonable unit to measure everything. For example, in my body, there are many chemical processes going on. The energy levels are of the order of, okay, few electron volts. So if a photon comes in and hits me with an energy of 2.5 electron volts, okay, it's just at the limit of making some possible chemical changes. Okay, anything much higher will go into the ultraviolet, which definitely is harmful. Anything lower, which is infrared and lower and all those radio waves, etc., they are harmless. Okay, so if you are worried about what your cell phone is doing to your brain, I am sure you are not too worried, because otherwise you wouldn't use it that much. But you can just estimate it. Well, if you have 500 nanometers here or half a micrometer, do you know the length of the radiation that comes out of your cell phone? It's approximately the size of your cell phone. Okay, so let's say 5 centimeters. So what is the factor here? If you go from millimeters to centimeters, so it's something of the order of hundreds, right? So the energy of the photon that comes out from your cell phones, okay, is going to be 100 times weaker than that. In fact, I may have, is that correct? Correct me. What is 500 nanometers, 5 centimeters? In fact, this is 0.5 micrometers, right? So this is 10.
Minus 4.
10
to minus 4 times 0.5.
Okay, 10 to the minus 6, 10 to the 6, 4, is that correct? Yeah, approximately 1,000 times. Okay, so the radiation that comes from your cell phone has photons with energies of microelectron volts. Okay, so there's nothing no harm that they can do to you chemically. Of course, if you put yourself inside a microwave oven and heat yourself up, of course, it's a different story. But just by photons, that's what you get. All right, so how are we doing on time? All right, so this is for the photon. The photon has then a wave function, let's call it that, which is of this form. So in physics, we don't use sine and cosine that much because we know that this exponential representation takes care of sines and cosines together. So instead of sines and cosines, I'm going to write this as I times k, well, careful, p over h bar x minus e over h bar t. So that's the photon wave, okay? So the wave, if you take the real part, it's the cosine omega t function, or if you take the imaginary part, it's the sine function, and we'll give you that, okay? For electromagnetism, we don't have to work with complex numbers, but again, for some cases, it makes our life easier. Now, for the electron, it turns out that the psi is exactly the same. Okay? For a non-relativistic and for this course, we'll mainly concentrate on non-relativistic electrons, okay? We will not look at relativistic stuff in this course, which is a whole different game. Okay, so it's the same equation, it turns out, except that E here is equal to momentum times C, but E here is equal to P squared over 2M, and it corresponds to the kinetic energy. Okay, so this is corresponding to a free electron. Okay, free electron means no potential energy. by the way, this is also free photon, okay? If you put the photon inside the box, then of course you get different types of functions. All right, so this is our psi. It turns out to be our psi. Okay, so this is how the theory is constructed. Okay, there's no reason why this has to be this thing. Okay, people playing around with these things, Heisenberg and Schrödinger, okay, played around with what mathematical evidence they had, and they came up with this form for the wave function of a free particle. Now, then, okay, Mr. Schrödinger thought, well, how can I now construct a differential equation? The Schrödinger differential equation. Normally, you see, we are given a differential equation and we try to solve it. But here, we are, okay, we have this result and we are looking for an equation whose solution will give us that. And you can convince yourselves that if I just take I times h bar and differentiate psi with respect to time, what does it do? It brings down, okay, so, well, minus I over h bar, okay, from this differentiation, I have this I h bar still, times, okay, E over h bar, which comes from the derivative. I'm sorry, just the E, okay, because I have taken I over h bar here, times the psi itself. Okay, so h bars and the i's cancel, and I end up with E times psi. Well, E is just p squared over 2m times psi. So I now want to also differentiate with respect to x so that I get a differential equation in x and t. How can I do that? Well, if I differentiate with respect to x, you see I can bring down p squareds. In fact, if you look at minus h bar squared over 2m times del squared psi del x squared, so differentiate with respect to x twice, it will bring down I squared, p squared, which is exactly what I want. Okay, so that's going to be p squared over 2m psi. Very nice. They are equal. So this says that I have this I h bar del psi del t is equal to minus h bar squared over 2m del squared psi del x squared. Okay, so I have now this equation which sort of seems to be consistent with this representation. Obviously, I can write infinitely many equations which will generate this, okay? But it turns out that this is the true one. This is the correct one, okay? This is when there's no potential energy, so I have run out of time. Next time we start, I'll just go over this argument one more time, and then we'll look at the Schrödinger equation, and then at that point we'll take that as given and then see what its consequences are. Okay, any last minute questions?
Can you also talk about its relationship with Hamiltonian formulation of classical mechanics?
No, it's not really relevant to our topic here. Okay. Okay, so I'll see you guys when?
Monday.
Really? Okay, Monday, yes, Monday 3:30. Okay, again in this room.